Hello again, my dear students. Now it's part number 2 in the BJT lecture. In this part, we are going to solve 3 examples mentioned in the lecture related to the DC analysis of the BJT circuits. Let's now start with example number 1, where we have our BJT transistor. It's a NPN BJT transistor because, as you can see, the current is going to the emitter. Here is the collector, and here is the base, as you can see. Here we have a battery connected with 4 voltage. Here we have a resistance, and then connected this, and this is a ground. The resistance here is 3.3 kilo ohm. Also, we have another supply in this direction. And we have another resistance in the collector. The upper resistance is 4.7 kilo ohm. And this voltage is 10 voltage. This is the configuration we have for the problem. As a given, beta is equal to 100. And what is required is to calculate all voltage and the current in this circuit. I mean, we should calculate the base current, the collector current, the emitter current, the VPE, the VCE, all voltage and current in this circuit. So now let's start solving this problem. The first step in solving any DC analysis BJT circuit is to start from the base. Here you can see that we have a loop. We can make a KVL in this loop, and we can say that -4 plus the voltage drop here, which is VPE, plus the current flowing in this resistance, which is IE times RE, is equals to 0. Okay, then -4 plus VPE plus IE times the resistance RE, which is 3.3 K, is equals to 0. Okay, now we have two unknowns, but remember, in order to make this transistor on, the voltage VPE should be equals to 0.7 voltage, which is the voltage drop to make this junction forward. So assume BJT is on, then VPE is equals to 0.7. So you can say -4 plus 0.7 plus IE times 3.3 K is equals to 0. Here you have one equation with one unknown. The unknown is IE. You can simply calculate IE. You can say IE equals to 4 minus 0.7 over 3.3 K. So IE is equals simply to 1 milliampere. This is the emitter current. Now you can calculate also different types of currents. If you remember from the lecture, the relation between the emitter current and the collector current is alpha, and the relation between the collector current and the base current is beta, and alpha equals to beta over beta plus 1. So with beta equal to 100, I can say that alpha equals to beta over beta plus 1, which is 100 over 100 over 101, which I can say simply it's equal to 1. If I can assume that alpha equal to 1, that means that IC is directly equal to IE equals to 1 milliampere. Now I know that IC equals to beta times IB. Beta is equal to 100. This means IB equals to IC over beta, which is 1 milliampere over 100, which will lead to 0.01 milliampere. Now I calculate I base, I calculate I emitter, I calculate I current, then I have to turn to the voltages. Here we know that the voltage here is 4 and the voltage here is 3.3 because the voltage drop here is 0.7. The voltage drop across the VPE junction is 0.7. So if this voltage is 4, simply the emitter voltage is 3.3. But what about the collector voltage? We need to know the collector voltage. Now we know the collector current. So we can calculate the collector voltage because simply the current flowing here, IC, multiplied by the 4.7 kilo ohm is equals to the 10 minus VC. So 10 minus VC is equals to the 1 milliampere times 4.7K. So VC equals to 10 minus 4.7K. Or sorry, 4.7 voltage. So it's milli times kilo, which is voltage. So 10 minus 4.7, that's why VC is equals to 5.3 volt. This is very, very, very important that you have here to stop, wait, and think. The voltage here is 4. The voltage here is 5.3, 5.7, I think, yeah, 5.7, 5.3, sorry, 5.3. Voltage is 5.3. Yeah, so this is 5.3 and this is 4. So now we are right. This is a reverse bias junction. And this is an active mode because you have one forward junction and one reverse junction, and then it's an active mode transistor because the voltage in the collector is greater than the voltage on the base, which is a condition, if you remember, for an active layer transistor. So this was the first example. We calculate all type of currents, we calculate voltages everywhere, and we make a full DC analysis for the circuit. And now we have a complete circuit. Now let's turn to the example number 2. Again, in the same lecture, example number 2, you will find something like that. Again, it's an NPN transistor. We have here 6 voltages applied. As you can see here, we have a resistance with 3.3 kilo ohm to the ground. This is the emitter, this is the base, this is the collector. And we also have an upper resistance again with 4.7 kilo ohm, and we have a 10 voltage here, plus 10. So it's typically the same like the first example, but with replacing the DC supply with 4 voltage, if you remember the previous example. So we replace this 4 voltage supply with another 6 voltage supply. That's all. So let's start solving the equations. First, we will say that we will make a KVL here. Then -6 plus VPE plus IE times 3.3 kilo is equals to 0. Again, here we can say that VPE is equals to 0.7 to make our transistor on. Now, we can say that IE is equals to 6 minus 0.7 over 3.3. Here is K, of course. So, this will result with a current on the emitter with 1.6 milliampere. Great. So we have the emitter current of 1.6 milliampere. Let's continue. So we know now the collector, the emitter current. We can say that the emitter current and the emitter current is roughly equals to the collector current. By the way, in this example, also beta is given with 100. It's a typical example like the first one, but with only replacing the 4 voltage by a 6 voltage. So beta is given. So IE is equal IC equals to 1.6 milliampere. Now the current or the voltage drop on this resistance is basically 4.7K times 1.6 milliampere, which is equals to the 10 voltage minus VC. So 10 minus VC is equals to 1.6 milliampere times 4.7 kilo. Simple like that. This simple equation, you can calculate VC. When you calculate VC, you will find that VC is equals to, this is very important, you will find that VC is equals to 2.48 volts. So here we have to wait and see. Now, let's think. This voltage is 6 voltage. Here we have a drop of 0.7. So this voltage is basically equals to what? It's equal to 5.3 voltage to make this transistor on. We calculate this voltage. We find that this voltage is equal to 2.48. That's right. Okay. 2.48. Yeah, that's right. So 2.48 and 6 voltage. Oh, now this junction is no longer a reverse junction. The voltage on the base is greater than the voltage on the collector. So it's now a forward biased junction. This is a forward biased junction. So this transistor is working as saturation. It's not working on active mode. So this assumption is wrong. IC is not equal I. I can make it when it's an active mode, but when it's a saturation mode, I cannot make it. So what should I do? Let's now replot the graph or the circuit. We have here the 6 voltage. We have here our transistors. This is the 3.3K. We are sure that this is 6, and we are sure that this is 5.3. Because here, this is a condition again for saturation to make the base emitter junction is full. However, what about the remaining? We know that this is 10 voltage. We know that this is 4.7K. Here we have to use what's called the VCE SAT, if you remember the lecture. In the lecture, I told you about the VCE SAT. I told you that please wait until we go to the problem to understand. Now we have what's called the VCE SAT. Usually we say that at saturation, VCE SAT is equals to 0.2 voltage. I mean, VC minus VE at saturation equals to 0.2. You know, you are quite sure that VE is equal to 5.3. Then VC is equals to 5.3 plus 0.2, which is 5.5 volts, which is totally different with respect to the one you calculated here, because this was wrong, because you make IC is equals to IE, which is not the case when it's a saturation. Okay, now you calculate the new VC. Now you know that this voltage 5.5. And you can now calculate what's called the IC. That's right. IC here is doable because 10 minus 5.5 equals to 4.7 times IC. Very simple. The voltage drop on the resistance, 10 minus 4.7 equal the current. So by this equation here, of course, it is 4.7K. So by calculating here, you will find that IC equals to 0.96 milliampere. Now, please recognize the difference. IC is equal 0.96 milliampere. IE equal 0.6 milliampere. So IC and IE are no longer equal. So we have IC equal 0.96 milliampere. We have IE equal 1.6 milliampere. Now we can apply the general equation, IE equal IC plus IP. So the base current is equals to 1.6 minus 0.96, which is equals to, let's make it, which is equal to 0.64 milliampere. This is the base current. So in this saturation again, please remember, this is a saturation case. In this saturation case, we can calculate what's called a beta force, or sometimes we can call it beta saturation, as you like, which is again IC over IP, which is 0.96 over 0.64, roughly equals to 1.5. So please take care. This is the new beta. The given beta is equals to 100, then we are right. The condition for saturation is that beta forces should be smaller than the normal beta in the active mode. We calculate beta is 1.5, however, the beta given is 100, then our assumption is right. So this is the second example where our BJT is working in the saturation mode. Please recognize it very well because this is a very important example. So again, we know that it's a saturation mode because when we assume first it's an active mode, we calculate VC, we find that VC equal 2.48 voltage. However, V base is equal to 6 voltage. So the base voltage is greater than the collector voltage, which means this is a forward bias junction and this is not an active mode case. Okay. Now let's turn to the final example in this lecture. A very, very easy example. If you find this example actually in the exam, you will be very lucky. It's a 10 voltage again. It's 4.7 again. And here is the 3.3, the typical example like the previous. Here, this is a ground, but one only difference. Now the base is connected to the ground. So it's typically the same. Beta equal 100 again. Typical, the same example. If you remember, in these three examples, we just change the voltage applied to the base. First, we start with 4 voltage, then 6, and now it's ground. The easiest one. So I'm sorry, just a disconnection. So this is 0 and this is 0, which means that by default, this base emitter junction is not in an active mode. This is not a forward bias. I mean, this is a reverse bias junction. So whenever you find that this is a reverse, then it's a cut mode, which means that IC equal IB equal IE equals to 0. No current will move in the BJT as far as this base emitter junction is not in the forward bias. So in general, we have 3 cases. First case, when the voltage on the base was 4 voltage, we find that we assume that it's on. We calculate the voltage in the collector. We find that this is a reverse bias. Then it's an active mode, and we solve the equation. The second, when 6 voltage is applied, we find that the voltage of the collector is below the voltage on the base. It's a forward bias saturation mode, and we solve it. Finally, when the base is grounded, no voltage, no current, it's a cutoff region. This is simply 3 mode of operation for a MOSFET. That's why this example is a very, very, very important example to understand the different modes of operation for MOSFET. Thank you very much. This is the lectures for this week. In the next week, we will have our lecture on the AC analysis of a BJT or bipolar junction transistor. See you next week and goodbye.